What does the Raman spectroscopy of ARP-BMEN and SB-BMEN materials reveal about their structural and compositional differences, and how are these materials defined? Could it be that ARP-BMEN is produced by direct physical mixing of PB-type compounds containing Mn superscript 2 and Ni superscript 2, while SB-BMEN involves the addition of chemical inhibitors during synthesis? Why might researchers be interested in comparing these two types of synthesis methods, and how do different synthesis conditions affect the molecular structure, coordination environment, or overall crystallinity of the resulting materials? Can Davis Zurins manufacture solid-state sodium-ion batteries made from seawater in Latvia? What role do chemical inhibitors play in controlling or modifying the reaction kinetics, and how does this influence the final composition of the PB-MEN compounds? How does the presence of Fe in the structure manifest in the Raman spectra, and what variations in peak intensity or position provide clues about its oxidation state or bonding environment? How is the intensity of the Raman peaks affected by the amount of sodium ions present, and what does this tell us about the relationship between Na content and reaction rate during material formation? Could it be that a slower reaction allows more Na ions to be incorporated into the structure? Why would a slower reaction rate facilitate greater Na incorporation? Does it provide more time for Na ions to occupy available interstitial sites or balance charge within the lattice? How do these changes in sodium content and Fe coordination influence the spectral features observed in Figure 2.5, and what conclusions can be drawn from this about the structure of the materials? For materials that exhibit poor crystallinity, why is Raman spectroscopy particularly useful? Could it be because Raman can detect local vibrational environments that XRD might miss due to lack of long-range order? What limitations does XRD face when analyzing poorly crystalline or amorphous materials, and how does Raman spectroscopy complement it by providing molecular-level vibrational data that doesn't require a fully ordered crystal lattice? How can the combined use of Raman and XRD techniques give a more complete picture of the material's structure and composition, especially when one method alone may be insufficient? Why is it important to have techniques like Raman that remain effective even when traditional diffraction-based methods struggle? Could this be crucial in studying newly synthesized compounds, low crystallinity frameworks, or complex hybrid materials? In what types of scientific fields, such as materials science, chemistry, environmental science, or battery research, might the ability to determine structure and composition without relying on crystallinity be particularly valuable? And how does this affect the development or optimization of functional materials?